Okay, so yesterday we were talking about the inverse trig functions, and the inverse trig functions give you an angle in a certain quadrant that has that sine or that cosine or that tangent. And so this first part, they want you to consider these two statements and consider if they are equivalent. And so this first one is telling you to find all the angles, all the x's that have a sine of 1/2. And this is like all the x's, not restricted. And so P and Q would both have a sine of 1/2 because the y coordinate is 1/2. This one, however, is restricted. So out of those two, which would be the answer to x for that one? P. It would have to be the one in quadrant 1. It couldn't be the one in quadrant 2 for the inverse sine. So there's two different things. It's kind of the same idea, but whenever you see this notation, the inverse or the arc sine or arc cosine or tangent, that is restricted to certain angles. This one is telling you to find all of the angles. All right, and then so that's some more of that. And so some of the stuff that we're going to do, we're going to be finding the general solutions to a trigonometric equation. And so if you guys think of that unit circle or you think of a sine graph or a cosine graph, that pattern repeats over and over and over again. Sure. It repeats over and over and over again. So there is an infinite number of angles that have a sine of 1/2. Because you could have pi over 6, but you could also have 13 pi over 6. It would also have a sine of 1/2. So every time you add the period to an angle, it's going to give you another angle that has that sine. So what you do whenever you're given the general solution for sine and cosine, you find the angle on the unit circle, and you're going to add 2 pi k to it, where k represents any integer in the world. So that's how you can represent an infinite number of solutions, because there are an infinite number of angles that have a sine of 1/2. And then same thing for the cosine. You find for 1/2, you would find the angles on the unit circle that have a x coordinate of 1/2, which are these two. And then you're going to have to add multiple periods to them to represent all of them. And then tangent's different. Why is tangent different? The period of like the parent tangent function is pi. And so what you only have to use the top semicircle of the unit circle to get the tangent answers. And then instead of adding 2 pi k, you add pi k. All right? Because these angles just repeat again down here for tangent. If we had the tangent of pi over 4, that's going to be 1. And then down here is the exact same. 5 pi over 4 is the exact same tangent, which is 1. And if you add pi to pi over 4, you get 5 pi over 4. So with tangent, you only have to use the top part of the semicircle. I think it might say that here. Oh, no, it doesn't. But let's write a note. Top of the unit circle. So it's just going to be a semicircle. It's a unit semicircle for tangent. All right, so let's do some examples, and it's going to make more sense. Sometimes when I'm just saying a bunch of words, it's hard to make sense of it all. All right, so let's look at example 1. We have that the cosine of x is negative square root of 2 over 2. So we're looking for all the angles that have that cosine. So if we're looking at the unit circle, we want the x coordinate to be negative square root of 2 over 2. All right, so looking at the unit circle, what's the first x coordinate or angle you see that the x coordinate is negative square root of 2 over 2? 3 pi over 4. Now we have to represent all of the angles. So if I added 2 pi to this, or if I added 4 pi, or if I added 6 pi. So to that, I'm going to add 2 pi k. All right, and there's another one. What's another one on the unit circle? 5/4, thank you. And then to represent all of the solutions, I would add 2 pi k to that. All right, now I know that's kind of weird. We're going to keep going. You're going to be okay. All right, so for example 2, we want to find all the solutions to sine of x is -1/2. So if you're looking at the unit circle, what we want is for the y to be -1. What do y'all think? 3 pi over 2. And then to represent all of them, we have to add 2 pi k to that. All right, and then don't forget, tangent's different, but we're going to start off similarly. So we want to find all the solutions to tangent of x is 1 over the square root of 3. So we're only going to use the top semicircle. And what we want is to take the y-coordinate, multiply it by the reciprocal of the x-coordinate, and get 1 over the square root of 3. And for that to happen, what you need is for the x-coordinate to have a square root of 3. It will be in the numerator if you're looking at the unit circle. And when we do the reciprocal of that, it goes to the denominator. So exactly like she said, is going to be pi over 6. Now there's another one on the unit circle, but we're not going to use it. We only have to use this one. All right, and then because this tangent and the period of tangent is pi, we're just going to add pi k to that. All right, and then I said all those things, and then last class someone was like, well, what about 7 pi over 6? You could list it, but if I took pi over 6 and I added 1 pi to that, is it going to give me 7 pi over 6? It is. And so it's already in there, like it's counted with the pi over 6 plus pi. We only have to use that top semicircle. It's going to take care of itself. All right. Now we're going to do one that's slightly more difficult. And then we're going to do some that the setup is, or the ending is a little bit different. All right, so those ones that we just did, the trigonometric expression was already isolated. There was nothing around it. Now we're going to do some where it's not. So on example 4, the trigonometric expression is sine of theta. So what would you guys do with that 6? Because we want to isolate that. You would just divide by it. And then that's going to reduce to the square root of 2 over 2. All right, so we're going to go to our unit circle, and we're going to find the angles that the y-coordinate is square root of 2 over 2. So it's going to be pi over 4 plus 2 pi k and 3 pi over 4 plus 2 pi k. All right, so what questions do you guys have so far? Good. All right, so starting at example 5, the wording is a little different, but the biggest difference is it tells us to find all the solutions that are between 0 and 2 pi. And so that is just all the angles that are on the unit circle. So we're not trying to find every single one. So on these, we don't have to do any of the plus 2 pi k or plus pi k. We just have to give these angles. Does that make sense? All right, now the way this is written, do you think you are ever going to give an answer that is 2 pi? Because I put it on my unit circle. You wouldn't, because this does not include 2 pi. I don't need to add that. So you're just going to get basically 0 to 11 pi over 6. All right, so let's see. We are given two functions, and we want to find where they are equal to each other. So let's just set them equal to each other. All right, so this one's going to have a couple more algebraic steps at the beginning, where we have to isolate cosine of x. So we would subtract the 3 and divide by 2. And because we're told just to find the intersection between 0 and 2 pi, we would look at the whole unit circle and find all the angles that the x-coordinate is -1/2. So it looks like that's going to be 2 pi over 3 and 4 pi over 3. Okay. Okay, now sometimes the sine or cosine is squared, and so there's just some discussion about how to clearly communicate that in the notation that we're given. So what you really need to see is what's in this box. So there's two ways to write sine to a power. The whole sine could be in parentheses with the power on the outside, or the power could just be on the sine. Most of the time, this is how you see it. You just see the power on the sine. Now tomorrow on your assignment, there is one, it's a calculator question with a sine squared, or maybe cubed, I can't remember. So just know that in the calculator, there's no way to put the square on the sine. It just won't work. So just make sure you do the parentheses and the square on the outside. And we'll practice that some more. Okay. So let's look at example 6. We have this function g, and we want to find the zeros, and we're finding the zeros in just that between 0 and 2 pi, so just the unit circle. So how do you find zeros? Like, what would we do? Just set it equal to 0. All right, and then we would go ahead and subtract that 3. Divide by -6. And then what would we do? This is what sine squared is. What would we do to find what sine is? What if it would? Say what? Yeah, just find the square root. All right, and then when you find the square root to solve an equation, any type of equation, even a trigonometric equation, you do have to do the positive and negative square roots. All right, so sine of x is equal to the positive and negative. When you do the square root of a fraction, you do the square root of the numerator. So what's the square root of 1? And then you do the square root of the denominator. Now, I told you earlier, probably like last week or before, that in pre-calculus, we really don't care if there's a square root in the denominator. However, if you look at your unit circle, do you have an angle where this is the y-coordinate? All right. There is an angle that this is the equivalent version. Do you know what the equivalent version? Look at your unit circle. Do you know what the equivalent version of that is? Your choices are going to be 1/2, the square root of 3 over 2, or the square root of 2 over 2. It's okay. It's the square root of 2 over 2. Pi over 6 wasn't one of the choices. It's okay. It's fine. So you did this in Algebra 1. I think you might have done it in Algebra 2, but it wasn't a focus in Algebra 2. Whenever there's a radical in the denominator and you don't want it there, what you would do is just multiply by it. on the numerator and denominator because that's the same. Yeah, that's the same as multiplying by 1 because it's the same thing. So then in the numerator, it'd be 1 times the square root of 2. And then what's the square root of 2 times the square root of 2? 2. All right. So if you're doing these equations and you have the square root of 1/2, just know that that is the same as the square root of 2 over 2. So, are you okay? It's okay. It doesn't come up too much. It might be something on the ACT though. I don't know if they put radicals, simplifying radicals on there on the ACT or not. It's not a super big focus from this point out in your mathematical career. If you don't know how to do it, it's probably going to be okay. So if you have one where you have the square root of 1/2 and you're looking at the unit circle, I bet in your mind it's going to trigger that that's the square root of 2 over 2. So what we want on this one is on the unit circle, all of the angles that the y-coordinate is either positive or a negative square root of 2 over 2. So look at your unit circle, see what you think. There's going to be 4 answers on this one. It's all the power over 4 answers. Oops. So these ones where you do have the positive and negative, you're probably, if it's one of the slanted angles, you're going to have 4 answers. And they'll be related. Like they'll all be the pi over 4s, or they'll all be the pi over 6s, or pi over 3s. Okay, now example 7, we still have this interval of our answers, so it's just the whole unit circle. And we want to find when cosine squared of theta equals negative cosine of theta. So we're about to do something that you've definitely never done with trigonometric equations before. You have done them with polynomial equations. So for example, if this had been x squared equals negative x, what would you guys do? If we wanted to solve this for x. Anybody? Yeah, you get everything on one side so you can factor it. So that's what we're going to do. So whenever there is a cosine squared and a cosine, we can't do it like what we just did on example 6. We're going to have to get everything on one side and then factor it. All right, so I'm going to add that cosine of theta. Now we want, if you were ever solving by factoring, one side of your equation has to be 0 or it's not going to work out. All right, so in this case, we're going to factor out a common factor. What is it? Cosine of theta. Whoops, that should not be an equal sign. If you factor cosine of theta out of cosine squared of theta, what are you going to be left with? Yes. If you factor it out of itself, what are you going to be left with? 1. Good job. All right. So do you guys remember what to do after you factor when you're solving by factoring? If it's polynomial or trigonometric. If these multiply to get 0, then what does one of them have to be? 0. So if you ever multiply and get 0, one of the things you're multiplying by is 0. And so we'll set each of these equal to 0. And we get 2 less complicated equations to solve. So this first one on the left, the cosine is already isolated. So we're going to look at the unit circle for all the angles whose x-coordinate is 0. and that's going to be pi over 2 and 3 pi over 2. All right, and then this other one, I just need to move that 1 over. And we're looking for all of the angles that the x-coordinate is -1. And those are your answers. So those are the three angles that you could plug in and square and do negative cosine, and you would get the same thing on both sides of the equation. It's probably not something you ever thought you would be doing, is factoring trigonometric equations. I love it, actually. All right, let's look at example 6. So we have this interval, so that's good. We just have to find our answers from the unit circle. And we want to find where these two graphs intersect. So basically, we want to find where they're equal to each other. So we'll just set them equal to each other. And then on these quadratic trigonometric equations, if you have sine squared and sine, we are going to have to factor it. So we're going to need to get everything on one side so we can factor. And it's very similar to the last one. We're going to factor out a common factor. Right. This one's a little more complicated than the last one in that step. So when you factor the sine out of 2 sine squared, you still have that 2, but you only have the sine. And when you factor out of this, the sine just cancels out, so you still have a square root of 3. All right, so then I'm going to move over here. We're going to set each of those equal to 0. All right, on the first one, the trigonometric function is already isolated, so we can figure out our angles by looking at the unit circle for the angles that have a y-coordinate of 0. Right. 2 pi also has a sign that's equal to 0, but like I said before, it does not include it, so we're not going to give it as an answer. All right, and then this one, we're going to add that square root of 3. We're going to divide by 2. And then we are going to look at that unit circle for the y-coordinate to be the square root of 3 over 2. All right, so I get 4 angles. That would be the intersection point of those two graphs in that interval. All right, and then I wanted us to do one more together, so I just put it on the back. So these are basically the same directions we just had. We still have this interval, so we're going to set these equal to each other. And then because this one has sine squared and sine, we are going to need to get everything on one side so we can factor it. Right here, are you going to check out before this class tomorrow?
I'm coming back to that. Oh, this
is where tomorrow. Okay, so I meant to ask you this, but I didn't. There is no common factor this time, so we're going to factor it like a trinomial. And so it's kind of cool. What we put here and here needs to give us sine squared of x. So what do y'all think? Sine of x and sine of x. Good job. All right, and then if this is a minus, what do we know about these? They're opposites. Nice. So one will be a plus and one will be a minus. All right, and then the numbers, I need to multiply to get the -3 and then subtract to get the 2. So it has to be 3 and 1. Which one needs to be negative? The 3. Nice job. Oops. All right, and then we'll set each of those equal to 0. And then both of these, I need to do one step to isolate the trig expression. So on the first one, I'll move that 1 over, and then I'm looking at the unit circle for a y-coordinate of -1, and that is when the angle is 3 pi over 2. All right, and then on the other one, I'm going to add the 3. Is it possible on the unit circle for the y-coordinate to be 3? What's the radius of the unit circle? 1. So for the y-coordinate to be 3, that's impossible. All the points are 1 unit away. So this is not possible, and that's okay. It happens sometimes. So our only answer is the square root of 3 over 2. So the largest value your sine and your cosine can both be is 1. It can never be bigger than 1. They can never be less than -1. All right. What questions do you guys have?